Have you ever stopped to think about, well, thinking? I mean, what is a thought really? Not in some philosophical abstract way, but physically. Like, what's it made of? Turns out the answer is all about the brain's electric secret. We're going to dive into how the basic laws of physics are what power the most incredible thing we know of, your mind. So let's get into it. Okay, so here's the game plan. First, we'll tackle the big idea, the brain's electric secret. Then we're going to zoom way in to look at the neuron's tiny battery. After that, we'll see how that battery creates the spark of thought and how that spark jumps from one cell to the next. And to wrap it all up, we'll pull all the way back to see how all this tiny physical stuff adds up to, well, consciousness. All right, first up, the brain's electric secret. This is where the world of physics smashes right into the world of thought.
Seriously, though, what is a thought? Is it a voice in your head? A sudden picture? It feels almost magical, right? But believe me, the reality is way, way cooler than magic.
And this is the big secret. The answer isn't just in biology, it's actually in the fundamental laws of physics. To really get it, you have to stop thinking like a biologist for a second and start thinking like a physicist. And that brings us to this cool field of study called cerebral biophysics. It's a fancy term, but all it really means is looking at the brain as a machine, a super, super sophisticated machine that runs on electricity and chemistry. And that's exactly the lens we're going to be using. Okay, so if the brain is a machine, what are its parts? Let's zoom way in on the most basic piece. We're talking about the neuron's tiny battery and how your brain actually stores power. So let's dive in. Get this. You have about 86 billion neurons in your head. That number is just staggering. And every single one of them, every single brain cell, is basically a tiny living battery. So the question is, how on earth does it hold a charge?
Well, it's actually a pretty simple and brilliant idea. Think about a regular AA battery, right? Has a plus end and a minus end. A neuron does the exact same thing. It works really hard to pump positively charged things, these little particles called ions, outside of itself. So what you end up with is a bunch of positive charge on the outside and a net negative charge on the inside. That difference, that separation, that's potential energy. It's a stored charge ready to go.
And this simple fact, this electrical gradient, is absolutely everything. It's the source of the power. It's like a coiled spring, just waiting for the right moment to snap. This isn't just some random thing the cell does. It is literally the power source for every single thought, feeling, and action you'll ever have. Okay, so we've got 86 billion tiny batteries, all charged up. Now what? How does that stored energy get used? This is where it gets exciting. Let's talk about the spark of thought, a process called the action potential. So think of a single neural signal as having 4 key moments. First, you have the resting state. The battery's just sitting there, fully charged, waiting. Then step 2, a signal comes in from another neuron and pushes it over a threshold. It's like flipping a switch. And that's step 3, the spike. All these tiny little gates, these ion channels just fly open. Positive ions flood in, creating this lightning-fast electrical spark that zips down the neuron. And then just as fast, step 4, it resets. It kicks those positive ions back out and recharges, getting ready for the next one. And when I say lightning fast, I'm not kidding. This spark can travel at up to 268 miles per hour. That is the literal speed of thought. It's why, when you touch something hot, your hand pulls back before you even consciously feel the pain. That's not magic, that's just pure physics happening at incredible speeds. But of course, a single neuron firing isn't a thought. You need a whole network of them talking to each other. So, how does that signal get from one neuron to the next one? Let's figure out how they bridge that neural gap. So that super fast electrical signal gets to the end of the neuron and it hits a wall, a gap. See, neurons don't actually touch each other. There's this tiny, tiny space in between them called a synapse. And electricity can't just jump across empty space, so the brain has to get creative. And its solution is pretty amazing. To get across that gap, it's called the synaptic cleft. The brain switches from an electrical message to a chemical one. The main players here are neurotransmitters. You've definitely heard of these. Things like dopamine, serotonin. They're the chemical messengers. They get released, float across the gap, and then they lock into little receivers on the next neuron, kind of like a key fitting perfectly into a lock. So that's the trick. The electrical spark gets turned into a chemical message just long enough to cross the gap. And once enough of those chemical keys find their locks on the other side, boom, they kick off a new electrical spark in the next neuron. It's this incredible, elegant relay race, switching back and forth between electricity and chemistry. All right, we've gone super deep into the weeds looking at the tiniest parts. Now it's time to zoom all the way back out and see the big picture. Let's connect these tiny physical events to the grand idea of consciousness and see why this little circuit matters so much. So here's the crucial point. One single spark isn't a thought, right? But trillions of them, firing in these vast, intricate networks, that is the symphony of your mind. It's all about scale. You take these simple, predictable rules of physics and you repeat them 86 billion times, and something new, something incredible emerges from it. Consciousness. Your personality, who you love, your wildest dreams, it's all built from these tiny little sparks. And, this isn't just some cool thought experiment. Understanding this stuff has huge real-world impact. It helps us figure out what's going wrong in diseases like epilepsy, which is basically an electrical storm in the brain, or Alzheimer's, where those connections start to fail. It's the blueprint we use to design better artificial intelligence. And maybe biggest of all, it gives us a real path to start tackling the mystery of consciousness itself. So that leaves us with a pretty mind-bending question to chew on. If your mind, your sense of self, your you-ness, is really the output of a physical electrical circuit, well, where do we draw the line between the biological machine in your head and the silicon machines we're building? What's the real difference? It's a huge question, and it gets right to the heart of what it even means to be human.